2, 1. Alright, here we go. The first previously recorded lecture for Complex Variables Math 365 here in spring 2023. And hopefully the only time we have to do this, but life gets in the way sometimes. Alright. Okay, so plot for today. So we're jumping into 1.6 out of our book, so the last part of Chapter 1. And this is going to set up the stage for a lot of what we're going to be doing for essentially the rest of the course. Because it turns out that for complex variables and complex valued functions, we, of course, want to start calculusizing all of these things, so taking derivatives and integrals. And it turns out that we're going to do this a little bit in reverse. Rather than starting with differentiation and then getting into integration, we're rather going to talk about how we integrate complex functions, because as we're going to see today, some of the integrals are a little, they're fun to see. But as we're going to discover, the differentiable complex valued functions are going to have incredibly nice integrals. Not to spoil anything, but basically the answer is always 0 or 2 pi I. So, alright. But before we get there, and talking about differentiable, and specifically what are known as analytic functions, we first need to talk about, well, how does integration of complex functions work? Alright. So, let us think about integration for a moment, as we normally have it, which is integrating a real valued function. So, note that the integral is defined on an interval. So if I want a subset of the complex plane and have access to integrating, and my usual integral requires an interval, it probably makes a lot of sense that the thing we're going to focus on is a subset of the complex plane that is essentially defined via an interval, and we're going to call these things curves. So a curve in the complex plane is precisely a collection of points that look like follows. So there is some function x and some function y describing the real and imaginary parts, and we'll use z to just generally indicate a complex valued function whose inputs are coming from an interval ab. Alright, our book uses gamma to separate the difference. I just like using z of t to be like, z of t is the collection of point z with this parameterization here. But our book uses gamma to kind of differentiate, but just noting. Alright, and as I've already let slip, note that, right, again, this is an algebraic description of something that we can actually think about as a element of R2, right? It's a collection of ordered pairs, x and y, as follows. Okay, so again, this is going to allow us to jump back and forth between the complex plane and R2, and speaking of R2, we took Calc 3 before we got here, and hey, parametric curves, yeah, I wonder if we integrate on those things or something. Yes, alright. Okay, so let's get some quick examples of such things. So we're got things just keeping our head as we work with these. So the natural thing is the unit circle, the collection of points of the form cosine of t plus I sine of t. Note that I could also write this as e to the I t if I wanted to, but keeping it broken into its real and imaginary parts is going to be useful. So, alright, right, and right, this is just the usual parameterization of the unit circle. And again, right, you can think of it as the collection of ordered pairs cosine t sine t. For a more exciting one, let's, in our brains, think of the triangle that has corners at 0, 1, and I. And I thought I fixed this. Why is this all screwed up? And the parameterization for this note is done piecewise. Alright, hold on, it'll fix itself in a moment here. There you go. I thought I had that fixed. I saw it being wrong before, and I thought oh god, anyway. Alright, what are we at? Minute 4, and it's already effed. Good job. Alright, so another example, imagine in your brain the triangle that has corners at 0, 1, and I. So, again, in R2, the point 0, 0, the point 1, 0, and the point 0, 1. It can be described piecewise, where we go from 0 to 1, and that's traced out by just having the parameter run from 0 to 1, no imaginary part. And then we go from 1 to I, and the trick here is this particular parameterization. Note that when you plug in t equals 1, there's no I, and there's precisely 1. And when you plug in 2, you have I and 0 here. Yay. So, in general, when you're trying to connect, create a line attaching 2 points, you usually do some sort of setup like this. Right, and then, so this part here traces out from 0 to 1, then we go from 1 to I, and then we go back from I to 0, and this one's pretty easy to see. Plug in 2, you're at I, and plug in 3, you're at 0. Well, there you go. Alright, and these two are pretty thematic for most of the curves we're going to encounter. They're almost always going to be circles of some sorts, or triangles, or later on we're going to see a parameterization for a square. So, basic shapes, although obviously we can, this definition is allowing for some pretty wild shapes, so depending on how crazy you want to make your x and y, and again, note this is revealing that we can piecewise do things as well. Alright, so the word curve we're going to use a lot, and we're going to throw other words in front of the word curve because, there's certain curves that we're going to be more interested in than others. Alright, so first off, a simple curve is one where the function z of t is one-to-one inclusively on the interval. So this allows the endpoints to be the same. So we call that closed if z of a is equal to z of b. So we want simple and closed to be used in tandem, so we don't require z of t to be one-to-one on the all of AB. So simple here is basically a nice, precise mathematical way of saying that my curve doesn't cross over itself, except allowing maybe at the endpoints. Right, so if the curve ends where it began. Right? Smooth is the usual way you would think you would define smooth. The derivatives exist and are also continuous, and in which case then we would define the derivative of the parameterization of the curve to just be the real part plus the imaginary part's derivatives. Alright. And piecewise smooth, as we just saw with the triangle, the triangle is not a smooth curve. There are corners to it, but it's piecewise smooth because you can break it up, and on each one of the intervals, I got derivatives, and they're nice and continuous. But at the corners, they don't necessarily work out there. Okay, so these are phrases we're going to throw around a lot, and again, simple, curves not crossing itself, close, curves ending where it began, smooth means what you think it should mean, and piecewise smooth also means what you think it should mean. Alright, so, and again, pretty much all of the things we're going to work with will always be simple, will always be piecewise smooth. Some of them will be closed, other ones will not. Alright, beautiful. Alright, so again, these are just words to keep in your mind. For the most part, right, the actual technical details of all of these are not going to affect us too much, but got to keep a nice little book of this stuff. Keep, keeping track of everything. Oh, look, 314. Isn't that interesting? Anyway. Alright, so something else that's going to matter with curves is the orientation of them, which is kind of a very difficult thing to get precise. So, broadly speaking, a curve is going to be oriented by the increasing t-values. And specifically, it means that when we do draw out a curve, there is a beginning and an end, specifically when t is equal to a and when t is equal to b. So, for example, the unit circle starts at the point 1, and then is traced out counterclockwise, and we end up back at 1 when we reach t is equal to 2 pi. Okay. Right, so that we can kind of clearly see in our heads and draw a picture of, like, the circle goes and it traces out counterclockwise. Right, there's a clear orientation to it, right, but if x and y are sufficiently complicated, orientation might start getting a little weird. But basically when we say orientation, we're just talking about, or there's a beginning and then there's an ending. And if there is a beginning and an ending, you can reverse it. So the reverse orientation of a curve is given by, you've got it parameterized out. You have a z of t describing it with an x and a y. Well, then we can reverse it by starting at b and ending at a. And that curve is denoted as negative z, as negative c. And the parameterization is given by, note z a plus b minus t as the input, but we define that as negative z. Which is a little annoying, because, right, you would think negative, would just negate everything, but it's not exactly how it goes. But that is the notation that is used for it. So, for example, the unit circle's reverse orientation. So, if you've already established the unit circle moving counterclockwise, you can get it to go clockwise by, well, plugging in 2 pi plus 0 minus t, and if you clean all of that up, you'll get cosine of t minus I sine of t. And again, because of the 2 pi periodicity, the 2 pi drops out, and then you have negative t. Cosine of negative t is, of course, just cosine of t, and sine of negative t is negative sine of t. Okay, so every so often we're going to pull this trick of reversing an orientation of a curve. Not too often right now, but as we go further, we're going to pull this off quite a bit. Alright, anyway, okay, so that's all we mean by orientation and reverse orientation. But of course, when we think about curves and orientation, we might think about things typically moving counterclockwise, and there's effectively a, like, oh, you have a thing on your left and you have a thing on your right. Part of your brain, when you're thinking of orientation, maybe kicks that in. And we can make that really precise, but we need a theorem to make that notion precise. Right, so see, this unit circle here, when moving counterclockwise, as you're moving along, the inside of the curve is on your left. But in the reverse orientation, the inside is on your right. It turns out you can make that very precise, but you need a big theorem for that, which is the Jordan curve theorem, which says that if you have a simple closed curve, so note simple, the curve does not overlap itself, close, it begins where it ends, this will cut the complex plane into two pieces. Both of them are open and connected, and one is bounded and one is unbounded. The bounded part being what's inside of the curve, and the unbounded being what's outside of the curve. Okay. Now note, all of these words we have defined, and they're all pretty reasonably defined, and the conclusion of this makes a lot of sense. Draw a closed curve in your brain that does not overlap itself. Right, you're going to draw like some circular blob, essentially. And no matter how complicated you make that blob, like have it as wind around a lot, it can never cross itself, and it's got to begin where it ends. And, right, very clearly, this should be cutting the plane into two open, disconnected sets. One the inside, one the outside. And this is like the go-to example, or at least one of the many, of, yeah, draw out a curve that begins and ends at the same spot and doesn't cross itself. You're going to cut the plane into two parts. The proof of this is obscenely difficult. So difficult that the original proof is still doubted to be even true. And we're never going to go through it. And in fact, this is a great example of a thing that was always told to me is true, and I've actually never sat down and worked out the details of the proof of it. I've glanced at it, and it's always like, oh boy, this is, what the hell's going on here? But, yeah. Anyway, so we'll just take this to be true. If you really want to prove it, go nuts. Right, but this is a great example of, like, obviously this is true, but, like, the proof, the details are so, like, muddy and gross for whatever reason. Which does happen, unfortunately, when we try to abstractify things in mathematics. Sometimes the proofs of very obviously true statements end up being, just weirdly difficult. But anyway, with this now, this gives us access to an inside and an outside, and thus we can have an orientation and call it positive. Basically, right, just think of the unit circle, as we trace it out normally, counterclockwise. On our left is the inside of the curve, and on our right is the outside. Okay, and, right, the way you precisely define this is that if you pick any point that's on the inside, and you look at the difference of that point and any point on the curve, well, then the argument increases by 2 pi as t increases from a to b. So, right, pick any point on the circle, and then, let t go from 0 to 2 pi, for example, well, then the argument is going to increase from 0 to 2 pi. Right, so the inside of the curve is on the left, and the unit circle is positively oriented. Right. Now, again, this is something that we're kind of just setting up, and we're giving a nice, precise definition for, but we're really not going to get that stuck on it too much right now. There's going to be moments where positive orientation matters, but for right now, this is just giving precise language to, right, just a very natural thing that we want to have in our head. Right? And we'll leave it at that. Okay. Alright, so that's the last thing about curves that we need to talk about, and now that we have curves nicely mapped out and a bunch of beautiful language for curves, we can now talk about integrating complex valued functions. Okay. Alright, so the complex valued functions we are going to integrate are always going to be defined on an interval, right? Well, the curves are defined on intervals, so right, the complex valued functions that we're going to integrate must be defined there. And again, that's because integration is defined on an interval. Now, of course, obviously, if you think about your calculus stage, you're like, well, I can integrate on, like, subsets of the plane, so maybe that's how I would want to integrate complex valued things, and it turns out, it's going to be better to stick to intervals here, and more worthwhile as we go further. Okay, so, the integral of such a thing is then just defined very nice and cleanly, the integral of the real part plus I times the integral of the imaginary part. Right? If you've got a complex valued function, we have access to its real part. Note this would be a real valued function defined on the interval AB. Likewise, this would be a real valued function defined on the interval AB. So I have access to their integrals, and so the integral for the complex function should just be what do you think it should be? Real part plus I times the imaginary part. Okay. And all of the usual properties of integration would carry over because I'm just integrating things. So the sum of two integrals is the integral of the sum, integral of a scaled function is the scaled integrals, the usual stuff. Yeah. So now that we've got a definition for the integral of a complex valued function defined on an interval, so take any complex function and a smooth curve parameterized by some z of t, then the integral on the curve will be what we would normally be doing, right? Replace z with the parameterization. Note dz would then be z prime of t times dt, and the curve goes from a to b. So the usual way you would integrate on a curve, as we saw in Calc 3, only now just written in terms of complex valued stuff. Okay. Now note here, this is a smooth curve. We could do this for piecewise smooth. You just have to cut it up and integrate in chunks, which, again, is totally fine. So note we are allowing ourselves to integrate on any piecewise smooth curve. Note, not closed or simple right now, just piecewise smooth. Good to go. All right, now that we've established the primary integration that we will be doing, integrating a complex function on a nice piecewise smooth curve, it is worth listing off, again, all of the usual facts about complex integration, just carry across as usual. Integrating a scaled function is the scaled integral, integrating a sum is the sum of the integrals. Integrating a curve that's been reverse-oriented gives you the negative of the original integral. You can work out the details. That's a simple u sub. Your book goes for the details of it, so check it out. And then as a final point, something that we're going to be surprisingly using quite a lot is the following inequality. The modulus of the integral of a function on a curve C is always going to be less than or equal to whatever the modulus is bounded by times the length of the curve. Which, right, is kind of a... If you think about it, it's just... Right, we saw this in calculus. This is essentially like slap the biggest rectangle you can that covers the function, then yeah, your integral never exceeds that. It seems like a very crude estimate, but it turns out to be quite powerful, so... Alright. And your book goes for the details again on all of these if you really want to see them. They're not particularly illuminating. Alright, but with all this in hand, talk is cheap. How do you actually do these integrations? Alright, well, the trick to it is to break it into real and imaginary parts, because, again, these integrals, we're basing them off of what we experienced from Calc 3, so just break it into real and imaginary parts and integrate thereof. So, for example, if C is a curve, alright, with parameterization x of t plus I y of t, and if we let f be in its real and imaginary parts, u plus iv, right, well then this integral in here, right, just break everything into real imaginary parts. This will be x prime of t plus I y prime of t. This will split into u of x y of t plus I v x y of t. Note, the real and imaginary parts can be thought of as functions from R2 to R. Okay, and then you just multiply everything out and group the imaginary parts and the real parts together, and that gives you these integrals right here. So if you want to actually integrate your complex valued function on your curve C, you get your parameterization in terms of x and y, and then you just split it up like this and you do that integral. Note, this is literally, these are just integrals with respect to t. Right, they're just Calc 1 integrals, that's it. Right, and recall that these integrals right here, if this was Calc 3, we would actually write them as follows. So, hopefully those things are looking a little familiar. All right. Okay, so there's the setup. These are the things that we will be doing. So with this in hand, we can actually do some actual honest-to-goodness integrations. So, for example, let's say we wanted to integrate e to the z, where c is the line segment attaching negative I to I plus 1. So first things first, you want to get your parameterization. Okay, and this one's pretty easy to cook up, because again, you're just connecting 2 points, and we already discussed how you can parameterize the line segment connecting 2 points as follows. But of course, we do want things to be written in terms of x plus I times y. So note in this case, x of t would be t, and y of t would be 2t minus 1. And note, these need to be nice and smooth, so they have to have derivatives, and the derivatives are pretty easily seen here. They're 1 and 2. Nice and easy. Oh, isn't that great? Okay. So, in order to actually compute the integral, so we've taken care of the curve part of it, so we've got our x's, and we've got our y's, and we got our derivatives. Now we just need our u's and our v's. Now recall e to the z, its real and imaginary parts are as follows. So the u part is ex cosine y, the v part is ex sine y, and so now if I want to actually do the integral, the parameterization went from 0 to 1. There's the real part, there's the imaginary part. We have our u of x and y, but note we got to replace our x with t and our y with 2t minus 1, and then we have to have our derivative of x here, which is 1, our derivative of y, which is 2, which is here. Note the minus sign, and again, that is just coming from I times I occurring. Explaining this part, and then again, you pop everything into the formula for the plus I part of the integral, and then you just do these integrals. And of course, by do these integrals, I mean I asked Wolfram Alpha what this stuff integrated to, and it told me what it was. And there you go. All right, obviously these integrals are not impossible to do, right? These would be integration by parts, but a by-hand computation here would probably be pretty tedious, but it's, right, the answer comes out pretty cleanly, so yeah, there you go. Not the worst thing ever. But, alright, hey, did our first complex integral. Okay. So, note that the curve that we integrated on had a definitive beginning and end point, and they were different from each other. Another integral that we saw a lot in our Calc 3 days was a curve where you began and ended at the same spot. That is a closed curve for us, and the very fancy integral with a circle in it to indicate that we started and ended, our curve started and ended at the same place. Now, hopefully, somewhere in your brain, you remember that this symbol converts very nicely, so long as the thing you're integrating is reasonable. So recall that if you've got a region with a boundary given by a closed piecewise smooth curve, and you've got two functions, m and n, with continuous partials, Green's theorem says that this integral converts to a usual double integral from calculus, where you're integrating over the region, and you do the partial of n. So note, with respect to the other variable, partial of m with respect to the other variable, and you take the difference of the two. Okay. Right, now, we're not going to derive Green's theorem. Your book goes through the full-out derivation of Green's theorem, so if you're really jonesing for that argument, go for it. There's a couple of ways to prove it. The standard proof is prove it for a triangle, and then go, well, any region can be broken up into triangles, so we're done. which I always thought was like a cheap thing, but anyway, oh god, I'm spilling coffee on myself. Great. All right. So this turns out to then be the key ingredient for us if we want to integrate a complex valued on a closed piecewise smooth curve, because most of the functions we're going to deal with are going to be nice and have continuous first partials. So we can then apply Green's theorem to do these sorts of integrals here. And now note, this allows us to convert everything into a double integral, and as we are about to see in a moment, most of the functions we're going to be interested in, things are going to kind of clean up very nice for us. So, for example, if we go back and write everything out, we know that this integral will break into these right here, and then by Green's theorem, we know that these have to turn into the following partials. Good stuff. All right. So note, this does reveal that when I'm integrating on a closed curve, I can actually just convert it over to just traditional double integrals as usual. Beautiful. All right, so let's wrap up today with an explicit example of this. And call it good. So, what's the explicit example we're going to use? All right, well, the region that we're going to do is something called the unit square. So, the square with corners at 0, 1, I, and 1 plus I. All right, and we'll let C be the closed piecewise smooth curve that forms its boundary. Now note, if you wanted a parameterization for C, there it is. Right here, tracing out from 0 to 1, tracing out from 1 to 1 plus I, tracing out 1 plus I to I, and tracing out I to 0. So note, this would be the positive orientation of the unit square. You could reverse this if you so wanted. All right, beautiful. Cool. All right, now that gives us our nice region and our nice closed piecewise smooth curve. What's a function that we would like to integrate? Well, let's get a little fun. Now let's do conjugation. Now note, the real part of conjugation is just the usual real part x. The imaginary part is, of course, negative. The imaginary part, which is negative y. Now note, we can compute the partials here, so the partials of u with respect to x and y, and the partials of v with respect to x and y as well. And hey, look at all this, just it's all nice constants. Isn't that wonderful? Okay. So, if I want to now do the integral by the work we did over here with Green's theorem, it's literally just plug and chug. So, pop everything in. Oh, hey, this part zeroed out. Isn't that convenient? And, oh, hey, look, we picked up 2. And, oh, look, I just need the area of the unit square. Well, good thing that has area 1, so this integrates to simply 2i. Beautiful. Now, note something really magical happened here. The real part zeroed out, because the partials there are behaving very nicely. Wouldn't it have been great if instead of -1 here we had +1, so that this difference ended up being 0, and I guaranteed that that integral was equal to 0? Yeah, that would have been really nice if that integral always just ended up equaling 0. Now, if we go back and look at it, we can see that there's kind of a way to ensure this integral always equals 0, because if these partials, let's say, for example, these were equal to 0, and if these were equal to 0, oh, that'd be this beautiful equations right here saying that, well, if you had a complex valued function and the partials always behaved in a certain way, that would guarantee that the integral on a closed piecewise smooth curve is always equal to 0, no matter what's going on. Man, I wonder if a function being complex differentiable guarantees that these things are zeros, and you always get that the integral of there is equal to 0, and that's like an absolutely fundamental fact and like the cornerstone of this entire course or something. Yeah, that'd be wild, right? Guess we'll find out on Thursday.